when we started talking about gases, we talked about the atmosphere. And I want you to remember that the atmosphere mostly consists of nitrogen and oxygen with small quantities of other gases. Each gas in the atmosphere exerts its own pressure so that the total atmospheric pressure is the sum of the individual pressures for each gas. Similarly, each gas in a mixture exerts its own pressure based on the number of moles of the gas and the volume of the container. And so this brings us to Dalton's law of partial pressure, and it says for a mixture of gases in a container, the pressure total equals the partial pressure or the pressure of the individual gases, depending on how many there are, right? So in the example here to the right, we can look, we have 8 moles of N2, 8 moles of O2, and we can also have 8 moles of gas if we have a mixture of N2 and O2, okay? The pressure itself depends on the total moles of the gas, not the identity. Okay. So that means the pressure total is proportional to the number of total moles. When we talk about this, it's important to understand the most abundant gas in a mixture will exert the greatest partial pressure. So let's look at mole fraction for just a second. The ratio of the number of moles of a component in a mixture to the total moles in a mixture is called mole fraction. And that's represented with an X. And we can say, hey, look, whichever individual component that we're interested in over the total, that gives us the mole fraction. When we look at the mole fraction in terms of pressure, we know the mole fraction equals the pressure or the partial pressure for whatever component, right? So if we have a mixture of two gases where we have the pressure total equals pressure 1 plus pressure 2, then that's going to be proportional to the number of moles of gas, right? By substitution, then, we can say, hey, look, when we're looking at the partial pressure, right, we can say the pressure of X, right, over the pressure total, okay? Just kind of like we did for the number of moles, right? We can come here and we can come here because these two are proportional to each other. And so what that means then is the pressure of one component over the pressure of the total equals the number of moles of the component over the number of moles total, right? So when we talk about this, we can rearrange this to say, hey, look, the pressure of X number of moles, whatever it equals the mole fraction, right, of X times the pressure total. As I mentioned, the partial pressure of a gas is proportional only to the mole fraction of that gas in the mixture. And so when we talk about this, right, that would be the mole fraction. Another consequence of this law is the partial pressure of a gas will change as the total pressure changes. So, for example, the mole fraction of O2 in the atmosphere is about 21%, regardless of altitude. However, as the altitude increases, the total pressure decreases, so the partial pressure and concentration of O2 also decreases. This means it's difficult to get enough O2 at higher altitudes. This is why high altitude climbers sometimes use oxygen tanks, like if you're going to climb Mount Everest. On the contrary, scuba divers must use a gas mixture with a lower mole fraction of O2 in order to maintain the appropriate partial pressure when submerged to depths where the pressure total is significantly greater. So, let's look at some examples. All right, so let's look at this example problem. A mixture of 6 grams of O2 and 9 grams of CH4 is placed in a 15-liter vessel at 0 degrees Celsius. What's the partial pressure of each gas and what's the total pressure in the vessel? So what we need to do when we look at this is we need to calculate the partial pressure of each gas using PV equals nRT, okay? So because we need to use PV equals nRT, we are given the grams of oxygen and methane, and we need to convert those to moles. So the very first step here is we are going to convert the mass to moles, right? And so the mole fraction of O2 equals 6 grams of O2. So 1. And so let's use the molar mass here. And that gives us 0.188 moles of O2. And then we need to convert to the moles of methane. We have 9 grams of methane. All right. And we come here and we say, okay, 1 mole of methane. There's 16.00 grams of methane. So we do this math and we get 0.563 moles of CH4. Okay. Now the second step here is we need to use PV equals nRT to find the partial pressures. And so to do this, what we're going to do is when we rearrange PV equals nRT to get the pressure, so we can get the pressure of O2 equals the number of moles of O2 times RT over the volume. And so we're going to plug in those numbers. So the number of moles we have is 0.188 moles of O2. We can know the gas law constant is 0.08206 liters times ATM over moles times Kelvin. And then we look at back up the problem, and it says the temperature is at 0 degrees Celsius. And so 0 plus 273 is 273 Kelvin. We need to divide by the volume. We look back up at the problem, and it's a 15-liter vessel. And so we're going to divide by 15 liters. Okay. When we do this math, we get 0.281 ATM. We need to do the exact same thing for methane. And so we come here and we say, great, that's 0.563 moles of CH4 times 0.08206 liters times ATM over moles times Kelvin times 273 Kelvin divided by 15 liters. Right. So we go through this, we do this math, and we get 0.841 ATM. And so now the third step of this, so those are our partial pressures. We've answered part of the question. We need to answer the full question. So we need to calculate the total pressure. And we know, according to Dalton's law of partial pressure, that we can add the two individual pressures together, the two partial pressures, to get the pressure total. And so we come here and we say that's great. It's 0.281 ATM plus 0.841 ATM, and that gives us 1.12 ATM. Honestly, I don't like to have favorites in chemistry, but Dalton's law of partial pressure is kind of my favorite. I think it's a very kind of neat phenomenon. Let's do another question, but let's look at mole fraction with this question. A study of the effect of gases on plant growth requires a synthetic atmosphere of 1.5 mole percent, carbon dioxide 18.0 mole percent oxygen, and 80.5 mole percent argon. Calculate the partial pressure of oxygen in the mixture if the total pressure of atmospheres is 745 torr. So we're interested in the pressure of oxygen. That's the partial pressure of oxygen. So we're looking at the pressure O2. And we can relate this to the mole fraction of O2 if we multiply the mole fraction of O2 by the pressure total. So how do we go about getting the mole fraction of O2 when we're given mole percent? Well, all you need to do is divide by 100 to get rid of the percent. So we have 18%. We'll divide it by 100%, and that gives us 0.180, and that is our mole fraction. So when we're looking at the pressure of O2, we just take the mole fraction, 0.108, and we multiply it by the total, which is 745 torr, right? And we do this, and you get 134 torr. Sorry, I had a cat that bit my pencil right then. So if the 34 looks weird, that's what was going on there. That's why I was giggling. Okay, there we are. You get 134 torr. So let's talk about the difference between real and ideal gases. We have been talking this whole time about ideal gases, and we've just treated all the gases as ideal because we have assumed, according to that kinetic molecular theory, that the volume of gas is negligible compared to the volume of the container, and that gas molecules act independently. There's no attractive or repulsive forces. While these assumptions are valid under normal conditions of temperature and pressure, they don't necessarily hold up under extreme conditions. At higher pressures, right, molecules are forced into smaller volumes. And at very high pressure, the volume occupied by the gas molecules is no longer negligible compared to the total volume. And so assumption number one is really no longer valid. And then as the volume decreases, the distance between the gas molecules decrease so that there's now significant interactions between the molecules. And so that means number five is no longer valid. So these factors lead to deviations from ideal behavior and require modifications be made to the ideal gas law. However, that is outside the scope of this course, so we're not going to go into it. I just wanted you to be aware that gases can deviate from this ideal model that we use.